Hello. I want to thank you for tuning in for this virtual presentation titled A Biomimetic Optical Approach to Skin Cancer Detection. My name is Kevin Major, and I'm a research chemist at the U.S. Naval Research Laboratory, and this is work done with my colleagues Jazz Sangera and Ken Ewing, both also at NRL. So when we think about it, it's kind of an interesting person to be speaking to a skin cancer session, right? A research chemist for the Navy. And the reason for that is what we do and what we're experts on at NRL is developing low cost, widely deployable infrared sensors to be able to discriminate between threats and non threats. And one of the things we've been looking at is different areas that we could expand this approach to. And one of the things we've noticed that we believe our approach could have some merit is looking at skin cancer detection. So I'm sure that most people in this audience understand that there's a strong documented need for the ability to detect skin cancer, and especially at the earliest stage possible. In fact, if you look in the literature, cutaneous malignant melanoma is still listed as one of the deadliest and most aggressive forms of skin cancer, and of course it is fatal if left untreated. Further digging into literature, though, you see that most of the non-invasive detection methodology is currently subjective. Specifically, what's used is the asymmetry, border, core, diameter, and evolution, or the ABCDE test. And this test is performed visually by a trained specialist, and it can exhibit a fairly high false alarm rate with only a moderate detection probability. And of course, the devil is in the detail with those numbers, where a highly skilled and highly trained dermatologist can have very good detection probability with this technique, whereas a general practitioner or someone less trained in the field may not be able to detect as well. So really there is a certain need and definitely would be a large benefit to a less subjective form of rapid and reliable testing of skin cancers. So since we're infrared sensing experts, what we did was we looked in the literature and we said, are people actually using infrared techniques to discriminate between cancerous and healthy skin? And we found a number of references where people are in fact doing this in both the midwave infrared from say 3 to 5 microns, as well as the long wave infrared 8 microns and further out. And what you can see is that there's approaches that have shown differences between, say, healthy skin and melanoma metastasis, as well as healthy skin and superficial spreading melanoma in different spectral regions. So because this technique can actually work, and we know that infrared sensing can be used, the question was then, well, can we apply some of our unique methods to be able to drive this technology forward and potentially result in a sensor that could actually be used in a clinical setting? So the technique I'll be discussing today is what we call our biomimetic sensing approach. And this method is based on human color vision. So if you look at the human eye, it uses three cone receptors, or one can think of them as optical filters, for high selectivity color vision. And these cone receptors are shown in this middle image here, where you can see the response of the three different cone receptors to different wavelengths of light. And depending on the interaction between the cone receptors and reflected or transmitted light, we can actually discriminate a huge number of colors. Some sources say over 100,000, some say actually over 1 million different colors. So what we've been doing is developing filter-based sensing methods to replicate human color vision, but now in the infrared. And our real goal is to reduce what we call the SWAP or the SWAP-C, so the size, weight, power, and cost, by implementing this biomimetic method. And importantly, the reason this really can reduce SWAP is that it only uses 3 optical filters and low power, commercially available off-the-shelf components. So the question is, can we actually use these methods we've developed to develop a low-cost handheld device for analytic detection of skin cancers? So some of the previous work we've done in this area to kind of describe the technique is what we've done is discriminated between different chemical vapors. So what I'm showing here are infrared spectrum for a chemical vapor set of acetone, hexane, and fuel oil, where fuel oil is the chemical of interest to be detected for, say, an ammonium nitrate fuel oil explosive. What we can do is then use some infrared filters on top of these infrared spectrum in the midwave, and we can generate these filtered responses. So I'm showing just one example here of the integrated, excuse me, of the filtered response for fuel oil with the filters of interest. Then we can integrate under these curves, and we result in what we call our tristimulus values. Now I want to pause for a second here to point out that while we're doing this modeling using infrared spectrum, the devices based on this approach will only have these three numbers. So this is why it's a really simple method to do the discrimination. So, these values are exactly analogous to the data that would be collected on sensors based on this technique. We can then generate a set of chemical vectors, and based on the good separation between these vectors, that means we can get good discrimination between our chemicals of interest. We then designed a laboratory-based biomimetic breadboard sensor, and importantly, what we did was we designed it using only commercially available off-the-shelf components. So we can see here you basically have a broadband infrared source, which is directed into a gas cell where it interacts with our vapors of interest. The light comes out the other side and goes to our bank of detectors with the filters installed in front of them. Again, very simple and uses only commercially available components to keep the costs low. We then assembled this biomimetic sensor in a laboratory, and an image of it is shown here. And what I'd like to point out is really kind of the size and simplicity of this whole setup. So the largest component for this setup is actually the vapor cell, which of course for a skin cancer detection method isn't really applicable. And really even this vapor cell is larger than we need it to be, and that's for very low level detection. Otherwise, it's just simply an infrared blackbody source and a series of commercially available detectors, which one can purchase online. And again, the output of this is actually shown here. So what we're demonstrating in this plot is that there's no chemical vapor in the chamber. We inject a chemical, so we see a very sharp change in response. And then as the chemical evaporates, those curves go back to the starting value. So this is all the data that actually the system outputs. So it's very simple. You don't need experts in spectroscopy to analyze the vibrational absorption bands or anything like that. If we then compare our sensor data collected on that breadboard to our calculated results, we can see very good agreement between the two techniques. So what I'm showing here, again, are the vectors for acetone, hexane, and fuel oil, where the solid vectors are the modeled data results, and the dashed vectors of the same color are those collected on the sensor, which I showed on the previous slide. The important thing to point out again is that we have excellent agreement between our modeled and experimental results. And what this means is that we can actually use this spectral modeling approach to determine how well an actual biomimetic sensor will behave when we are no longer collecting spectral data. One last thing to point out from some of our previous work is that in addition to those vapor phase studies, we also demonstrated discrimination of materials on surfaces, which of course is very applicable to a potential device for skin cancer detection. So what I'm showing on this slide is discrimination of 3 different explosive materials. And again, using a different set of filters, we can actually have good separation between these materials, which actually are quite similar even in their infrared vibrational absorption bands. And again, the key point is that we also can do this work for solids on surfaces. So the takeaway of our approach is that using only 3 optical filters, we can discriminate between chemicals with very similar vibrational absorption signatures. Importantly, the response of the system can readily be modeled using straightforward calculations. So we don't always need to have a device in place. We can use spectroscopic data to determine how well a device based on our method could behave in the future. The system has been shown for vapors, but importantly, it also has been demonstrated for solid phase materials, which would be applicable for skin cancer detection. So the question is, can we actually apply this method of detection to skin cancer? Now, we at NRL, of course, aren't experts in skin cancer detection, and we don't have really the resources to get samples or to work with patients or anything like that. So what we have to do is kind of go back and say, well, how can we get some samples to do some modeling and see how well this will work? So we go back to the literature, And what we did was we basically selected, so these are the same references that I showed at the beginning. And what we did is we said, well, let's select a couple of spectrum based on some previous work we showed actually at Photonics West last year, where we're actually trying to discriminate between, say, healthy skin and two different types of cancerous tissues, so melanoma metastasis and nodular melanoma from this reference here. So because this cancerous and non-cancerous skin exhibit different infrared spectrum, and we know previously that we can use modeled infrared spectrum to determine how well our biomimetic sensor can work, this was our approach to determine if we could actually develop a method that could discriminate between, say, healthy and cancerous skin tissue. So what we did was we took those spectrum from the literature, we digitized them and used a little bit of modification basically to get a normalized plot here. So you can see these are the same spectrum just in a slightly different format for the melanoma metastasis, the nodular melanoma, and the healthy skin. The other thing we need to do for our method is we need to have a series of test data to determine how well our sensor is working. Obviously, what you would really want are a number of different patients with a number of different lesions which you could test against. However, of course, we don't have that option. So what we did was we basically took our spectrum and we generated noise on top of it. So now we have some variation in our signatures which fall within this gray region. We can then use a database of commercially available infrared filters. So we go online and we say, what commercially available filters can we buy? Again, so we're not making anything bespoke to keep the cost down low. And we do an exhaustive search over our spectral region of interest using those filters to determine a set that can actually discriminate between our samples of interest. So this is the filter set which that exhaustive search resulted in. And there's more information about that in the associated preceding article with this presentation. But what you can see are that, perhaps just to point out one example, these green and blue filters are looking at a different absorption feature for the two cancers, which is not there for the healthy skin. So that's how this approach actually does work. And again, please see the preceding for a little bit more information about this, as well as associated references. Once we have those filters, we can then do our simple integration as we've done before to generate our vector space. So here's our vectors. And importantly, what you can see is that the healthy skin is well separated from both of the two different types of cancer. But also, and if you can see this more if I rotate the figure around, you actually get discrimination between the two different types of cancerous tissues. So that means that this approach could actually be used to maybe provide even a little bit more information potentially than just cancerous, non-cancerous. It could maybe give some guidance into different types of cancerous lesions, which could also be quite important from a diagnostic and treatment perspective. Then we take our test data, so again, using now our algorithm to generate additional noise onto our system. And what we can see here are basically the results. Now, rather than showing the vectors, because it kind of gets a little bit messy, I'm just showing the different vector components. So this top figure is the short filter versus the mid-wave filter. The second figure down is the short filter versus the long wave filter, and the bottom one is the mid filter versus the long filter. But really what to take away from this is that you get very good grouping between the different classes. So again, all the blue markers are for healthy skin, all the green markers are for nodular melanoma, and all the red markers are for melanoma metastasis. So you can see, again, good grouping between the different class or within a different class, as well as nice separation between the different classes. So there are some overlap, say, for instance, you can see in this top figure some points of healthy skin that overlap with the nodular melanoma, but overall we can separate quite well between the different classes. What this also allows us to do is a ROC curve analysis, so receiver operated characteristic analysis, which I'm showing on this slide here. So for those of you who aren't as familiar with a ROC curve, a perfect ROC curve would go straight up and straight over, because what that means is you have some value in your measurement where you can have 100% true positives being detected with 0 false positives. A ROC curve that just has a diagonal line, which goes straight from this point down at 0, 0 to up at 1, 1, that would result in a ROC curve that basically is no better than random chance. So as you see, as you get closer and closer to this 90-degree angle, you have a better ROC curve. And we're showing actually quite good results here for these 150 different test spectra that we generated. So just to pull out a couple of points here to kind of explain. So what we see actually is that we can get a true positive rate, say, of about 80% with a very low false positive rate of about 5%. And of course, we probably want a higher true positive rate than that. So if we have a true positive rate of about 98%, that results in a false positive rate of 15% for these calculations. So again, now these are just calculated results. We don't expect that a sensor would necessarily provide these types of metrics. But what this does show, and it does confirm, is that this approach can be used for detection of skin cancer, albeit on calculated modeled results from literature data. So what we really need to be doing is now taking this to the next step where we can hopefully get a get some samples of actual skin cancer to actually be discriminating and try to really build a device and test these metrics out. So in conclusion, we've demonstrated that our biomimetic infrared sensor is capable of discriminating between different chemicals, and it's based again on their variations in infrared absorption. But importantly, it's a non-spectroscopic method, and this dramatically reduces the cost and complexity to the end user. Because previously literature data identified that cancerous and non-cancerous skin tissues demonstrate variations in infrared spectrum, we believe we can take that approach and use our biomimetic method to see how well we can actually model results to that. And that's what we showed here, is that our calculations show that we believe this biomimetic sensing method is in fact capable of discriminating between cancerous and healthy tissue. And this is all geared towards the development of a potential low SWaP-C, so size, weight, power, and cost again, sensor for skin cancer detection. And of course, there's obviously more work that needs to be done in this area, and that's kind of one of the things we're interested in doing, is building collaborations, especially with this community, where we would actually have potential access to more realistic samples and more realistic data sets to test our methods out and develop an actual sensor for testing. But what we've shown here is that the approach certainly does seem to have some strong merit based on these calculated results, and is really ready to take the next step forward. So please do reach out to me if you'd be potentially interested in hearing anything more about this method, or if you would be interested in a potential collaboration in the future. I want to thank you again for your time, and please do let me know any questions in the online forum. Thank you.